Now being somewhat familiar with inductors and capacitors, let's put them together in an LC, or inductive-capacitive circuit. So here it is. We're going to begin with the capacitor charged as shown. We're going to analyze it clockwise and see what happens. So we have a current, an intermediate current that begins to flow. It's flowing the other way, counterclockwise. And that's going to produce an EMF that's opposing this current. So you're going to have a plus on the top, negative on the bottom. So we're going to start around here and do a Kirchhoff loop. Well, if it's plus here and minus here, we're going from minus to plus. So that's a rise. So we say minus L di dt because di dt is actually negative. The rate at which the current changes is going to diminish. So it's a negative rate of change. And so we have minus L di dt going around like this, and then we encounter a drop across the capacitor, minus Q over C, equals 0. Well, remember that I is dq dt. So di dt, divide both sides by dt, take the second derivative of the other side, dq squared dt squared. So now let's rewrite Kirchhoff. L d squared q over dt squared plus q over c equals 0. So d squared q over dt squared, if you rearrange, divide through by L, and we get this result, and that's pretty happy. The reason that's happy is because we're going to compare it with the standard formula, the standard equation that we encountered when we studied simple harmonic motion, which was the second derivative of position, or the acceleration. dx squared dt squared plus k over mx equals 0. This is the equation of a harmonic oscillator here. And as we see, our LC has the exact same form. Q and X, QX, right? So Q is like X. I takes the place of V. L, the inductor, takes the place of the mass. And 1 over C, there's 1 over C, takes the place of K, the spring constant. So initial conclusion that we can come to right now is that in LC circuit, the charge flow, the flow of charge, just like the velocity of the mass, so we remember X, we have X and Q connected. The derivative of X, of course, is velocity, and that varies sinusoidally in SHM. The derivative of Q is current, and so the current, or charge flow, varies sinusoidally as well. When you encounter problems with inductors and capacitors together, typically what you're asked to do is find the frequency of the oscillation, as opposed to the period, which was more typical with the spring-mass system, for instance. So mass spring LC, let's compare. We had position X, A cosine omega t. By analogy, in the LC circuit, we have Q equals maximum value of little q is big Q, cosine omega t. And then, of course, if we take the derivative of Q, we get I. And so that's just minus omega Q sine omega t. So there's our current. Now, omega was 2 pi f, which is the square root of k over m. You'll recall that. So by analogy, in the LC circuit, k is 1 over c, and m is L. So we have omega is 2 pi f, which is square root of 1 over LC. And that is the frequency of oscillation of an LC circuit. Quite simple and fairly important. Let's carry this analogy a little further. We have the mass on a spring, oscillating, spring constant K. We have the LC circuit, C and L. So, the kinetic energy on a mass spring, 1/2 mv squared. The magnetic energy in an LC circuit, 1/2 Li squared. Wonderful analogy. Remember, M is like L. V is like I. There it is. Potential energy. US, spring potential energy, 1/2 kx squared. The electric potential energy stored in that capacitor. UV is 1/2 q squared over c. Remember, K is like 1 over C. There it is. So now energy, 1/2 mv squared plus 1/2 kx squared is the maximum value of the potential energy. Let's do the same thing over with the LC circuit. 1/2 Li squared plus q squared over 2c is the maximum amount of energy, which is big Q squared over 2c. Now, again, M is like L. V is like current. K is like 1 over C. X is like Q. And then big A is like big Q. All right. If you know the equations for simple harmonic motion that we established with the spring mass system, if you can keep in mind the parameter analogies that are listed here, then you can write down the equations for the LC circuit. Not a problem. You don't have to rememorize, or memorize from scratch, I should say, all the equations for an LC circuit. They'll all transfer over by analogy. So let's finish the analogous features by writing the energy equations for both simple harmonic motion. 1/2 mv squared plus 1/2 kx squared is 1/2 ka squared. And the LC circuit, 1/2 Li squared plus q squared over 2c plus big Q squared over 2c. And recognize now that by looking at that energy equation, we can solve for V with SHM. We've done this. We get this expression where square root of k over m was omega. In like manner, the current, I, can be solved for algebraically, plus or minus square root of 1 over LC times big Q squared, square root of big Q squared minus little q squared, where the square root of 1 over LC is omega. Then, as we've already seen a little earlier, omega is 2 pi f, which is 2 pi over t, which is square root of k over m. Over here, omega is 2 pi f, which is 2 pi over t, which equals the square root of 1 over LC. Now, the most common form for regular simple harmonic motion is to discover the period, 2 pi squared of m over k, but in an LC circuit, we're generally looking for the frequency, which is 1 over 2 pi square root of 1 over LC. So there that is. Now, velocity is derivative of position. Current is derivative of charge. So, we know that for SHM, x we can write as a cosine omega t, which is a cosine of omega square root of k over m t. And for an LC circuit, q, the analogous quantity, is equal to big Q cosine omega t, which is big Q cosine of omega square root of 1 over LC t. Then V, the derivative, minus omega a sine omega t, where omega a is the maximum speed. In like manner, the current, minus omega q sine omega t, where omega q is the maximum flow of charge, which is the current. Then the acceleration, take the derivative again, and we get minus k over mx. The IDT is minus omega squared q cosine omega t, and that's minus 1 over LC times q. So there's all the connections between regular spring mass system, SHM, and the new LC circuit, SHM. And you can see how tight the analogies are, and you can see that you really don't have to memorize from scratch all these relationships. But I would encourage you to recognize these relationships. We need SHM for mechanics. You don't want to forget about that. And LC, the corresponding suite of equations and relationships for an LC circuit in E&M.